In Unit 9, we're going to be talking about transducers. Transducers are things that change energy or a signal. And information is also that same. Those are kind of used synonymously from one type to another. Okay, each transducer will have some kind of input signal. And then we'll have our box where we put the name of the transducer. And then some output signal. And we're going to draw lots of these boxes and these input and outputs today. Okay, so we'll replace the word transducer there with the name of different transducers. Transducers are useful in acoustics because it is the way that we record sound, it's the way we listen, it's the way we produce sound, it's the way we analyze sound, it's the way we store sound. All of those depend on different transducers. Okay. Acoustic receivers. Okay. For transducers that are acoustic receivers, the outputs or the input signal, transducers that are acoustical receivers, the input signal equals acoustical energy. Acoustical. I'm using signal and energy interchangeably. Okay. So what are some of our primary acoustical receivers? Examples, okay, would be microphones and our ears. Okay, they take in acoustical signals or sound. Acoustic generators means that the output signal is acoustical. Okay, and I'm not going to write the signal and energy every time as we go through this, but the output signal is acoustical. So examples of this, things that generate sound, right? This is what acoustic generators are. Things that generate sound. Examples would be our voice, loudspeakers, musical instruments, thunder, right? Anything that produces noise is an acoustic generator. Okay, so that's the first section of ideas there. What is a transducer and what are acoustic receivers and generators, acoustical receivers and generators. Okay, the second topic is this idea of analog signals versus digital signals. Analog signals are continuous. Okay, and digital signals are discretized, okay, which means they're broken into small chunks. If it is digital, examples of digital signals would be CDs. Okay, the CDs have discrete grooves, bumps and grooves that are then read by a laser. Okay, and then any file that is saved or processed by a computer, the signal is stored in discrete or small individual chunks, or as strings of zeros and ones. Okay, so that's where the term bits comes from. If you've heard of like bits per second or something like that for transfer rates. Okay, that is related to that. And we'll talk a lot more about digitizing signals, how that's done, what are the important things for sound reproduction and storage and things like that as we go along. Okay, so question number 1 says, Is the output from a loudspeaker analog or digital? Okay, so first you think, what is the output signal from a loudspeaker? That's the first thing to ask yourself, and that is an acoustical signal or sound. That's synonymous. All sound is analog. Okay. Question number 2, sound you hear from an MP3 file on your computer. Okay, sound equals analog signal. Okay, all sound is an analog signal. Now, the information, so the answer to that is A. Both of those is A. Okay, but the information stored in the MP3 file is digital. Okay. All right. Now, so what does that look like? Let's think about this. Sound you hear from an MP3 file. So let's start. Here we have the MP3 file. That is input. Okay, so this is a digital signal. That will be input to a digital to analog converter. That's a kind of transducer. And then, so that what that does is it takes a digital signal in, converts to the analog. Okay, and then that outputs an analog electrical signal. Okay. I'm going to run out of room if I write signal all the time. Okay, analog electrical signals, that's analog, that then is sent to a loudspeaker that then produces the acoustical signal, which is also analog. Okay, so usually these things are all contained in our phone or in our computer, and we don't think about the different processes that are happening. But today for our class, we are going to actually think about the chain of what has to happen for you to be able to hear the sound from an MP3 file, for example, and other things. Okay, we're going to come back to this in a little bit, but just to remember. Okay, so here's a hint. Sound is analog. Electrical signals are analog signals. Okay. Also, things stored on, so like records, they have a continuous signal, right? The needle reads all around it. So those have an analog signal. And tapes, magnetic tapes, are also analog. Visual things your eyes see. That'll also be referred to as optical sometimes. Okay, are analog. Okay, but the optical signals, but CDs store their information digitally, store digitized information. It's not a continuously varying bumps and grooves like a record player. It is actually digitized information. Okay. Okay, the next topic are 2 features about loud transducers that are really important, and we're going to talk about these more on another day. But just to give you an introduction today, we have number one is dynamic range. Okay, and that, as your handout says, is the amplitude range over which the linear response is achieved. Okay, so linear response means that if you double the input, the output doubles. Okay, and frequency content remains the same. You will just change the amplitude of the sound. Okay, so if you exceed the dynamic range on something, like is common in car stereos, if you turn up your car stereo loud, then you will have peak clipping. Okay, let's say you're looking at a time waveform, time varying or time dependent waveform, you know, like you might see on an oscilloscope, like you looked at on your learning activity. Okay. Then if you have a signal that has a low amplitude, it doesn't have to be a sine wave, but let's just say it has a low amplitude. Okay. Then if that is within the dynamic range of the loudspeaker, let's say this is the dynamic range of the loudspeaker, then all of that will just appear as that. But then if you, as you crank up the volume, now this is going to be tricky. I'm going to try to draw the same type of waveform, but just with a louder amplitude. Okay, pretend it's the same wave. It doesn't double back on itself. That would just be a louder signal. The blue one that I just drew, it would be louder. It has a larger amplitude, but it still is within the dynamic range of the loudspeaker. That would be something like, say, plus or minus 40 decibels. That's just an example. Plus or minus some number of decibels would be the dynamic range. Okay, and that's, you'll find this on things like microphone and loudspeakers, other components, electronic components that you would buy. Okay, but if your sound, same sound, we're just going to turn it up louder, and I'll try to draw it again. If it exceeds that dynamic range, okay, pretend like those zero crossings line up, then what's going to happen is that right here, your loudspeaker cannot actually produce that high amplitude because it exceeds the dynamic range. So it will produce this bolder pink signal. Okay. Even though it was asked to produce the thinner pink signal, it will only be able to produce this other one, which you can see is different. Doesn't have the rounded curves on the top. Okay. But it does this. This is called peak clipping. We will talk more about peak clipping another day when we talk about speech transmission and the effect this has on intelligibility. Okay, again, pretend these are the same wave, that they have the same zero crossings. Okay, but this pink signal, the amplitude has been turned up so loud that you have exceeded the dynamic range. You have peak clipping occur, which is what introduces that buzziness that you may notice when you turn your car speakers up too loudly. Things like that. So this pink signal exceeds the dynamic range. And the result of that is called peak clipping. Like I said, we'll talk more about that in another unit. Okay, so the dynamic range is the amplitude range in decibels over which you can faithfully reproduce the signal. about over which there is no distortion. Now, or very little. Okay, so that's the dynamic range. Now we're on to the frequency response. Okay, so the frequency response is the frequencies over which a transducer works well. So different microphones, for example, will have different frequency responses. Different loudspeakers will have different frequency responses. If you think of like a 5.1 or 7.1 something surround sound system, we'll talk more about this another day also, but just as a preview, okay, you would have so I'm going to write here the amplitude response. We're thinking now spectrum because we're doing frequency, right? So we have the amplitude on the spectrum over frequency. Okay, so if we think about as a function of frequency, what is the response of the transducer? So that's like, what does the transducer do to certain frequencies? Okay, and basically you'll have, if you think of a 5.1 surround sound, right, you would have your subwoofer, right, that would be over some low frequency range, able to produce all of those sounds really well, and these ones a little bit, but then it eventually rolls off nice and low there. Okay, so this would be like the frequency range where your subwoofer is very efficient at producing sound, and that's, you know, the subwoofer is designed for those low sounds, right? And then you would have like maybe your main channel, put it in a different color. So your main channel, you may want to capture the frequencies that are particularly important for speech. Okay, so then this would be like the frequency response, say, of your main channel. Not doing so well there on my drawing, but anyway, that might be what the main channel, it has certain frequencies over which you want to capture the sound. Okay, and then eventually you'll have over here your tweeters. You'll have some frequencies over which the tweeters work well. You're not asking the tweeters to produce low frequencies, and you're not asking the subwoofer to produce high frequencies. Okay, you have different loudspeakers that are optimized to produce different frequencies. Those frequency range over which the response is basically flat is what we will call the flat frequency response. Okay, and once it starts rolling off, right, then that wouldn't count anymore. These are just approximate, just kind of a cartoon. You can find actual pictures of these many places, including your textbook, when we talk about sound reinforcement. Okay. Okay. So examples of transducers. Pickups. Okay. These are used on electric guitars or any electromechanical instrument, meaning mechanical energy is being changed into an electro signal. Electric guitars are the most common example of this, and the one that we'll be talking about right now. So on a guitar, you have a metal string or a string with a metal core, okay, that's fixed at both ends. And then around where the hole would be in a regular guitar, you have these pickups. And the pickup has a magnet, which I'm doing in the dark blue here, surrounded by wire. Okay, So the green there is the wire. And this device, okay, is called the pickup. Now, the input to that pickup is the mechanical motion of this string. This string is vibrating, right? If you pluck it, you'll have a wave, a complex wave that'll travel down and reflect back and travel down and reflect back. And as that string moves in the vicinity of the pickup, it will result in a change in the magnetic field that will cause an electrical current to flow. So the motion of the string is the input. Okay. And that, okay, so, and then we're in the pickup. And what the pickup does is the change in the magnetic field causes electricity to flow. Okay, and that resulting electrical signal is the output of the pickup. Okay, but to be able to hear that sound, so what happens next? So that electrical signal will then go usually into an amplifier or pedals, effect pedals, right? Things like that, that will change the frequency or the time, or these are all different kinds of transducers that we'll talk more about when we talk about electric guitars. But then in the amplifier box, that newly modified electrical signal has to get sent to a loudspeaker to produce the acoustical signal, which is the sound that we hear. Okay, so we're used to these things all being in one box, but today we're thinking about them as separate pieces. Okay, so for an electrical guitar sound to be heard, this is the string of transducers. So for the motion of electric guitar string to be heard. Okay. Now, if you wanted, okay, well, we'll talk about that another time. But anyway, you could take that electrical signal from the amplifier, right? And you could also send that electrical signal to an oscilloscope. And then you would get a visual signal out. And that visual signal would show you the string motion versus time. Or how the string motion changes with time. Time varying or time dependent signal. And that's not how, that's how. So the visual signal would tell how the string motion changes with time. But to hear the sound, you have to connect it to a loudspeaker. Okay. But just to repeat, since I kind of got off there, the input for a pickup, go back to blue since I'm in pickup. Okay, so the input to the pickup box, the pickup transducer, is the mechanical motion of the string. Mechanical signal. Mechanical just is associate things with motion. And then the output from the pickup is an electrical signal. All right, let's do another. So now we have microphone. Microphone. The input to the microphone is an acoustical signal. It's the sound coming in, hitting the microphone. The output from the microphone is an electrical signal. How do I know that? Well, this particular microphone is a wired microphone, okay? So any sounds, any signals traveling through wires are electrical. Okay, now let's do another one. Now we'll do loudspeaker as our transducer. The input to the loudspeaker is connected to wherever the signal is coming from by a wire. So it will be electrical signal into the loudspeaker. There's mechanical motion inside, but that's not the total output. The output signal is acoustical. That is the thing that is our acoustical generator in most of these cases. Okay. All right, so now let's do an oscilloscope. The input signal for an oscilloscope is, again, an electrical signal. Think of an oscilloscope kind of as a standalone box that's plugged into a wire, into whatever it's getting the signal from. Okay, could be a pickup, could be a microphone, okay, could be a computer file or whatever. But the oscilloscope is taking an electrical and then displaying a visual or optical signal. Okay, visual things are a small portion of the optical spectrum. These are also electromagnetic waves or light. Okay, but we'll use visual and optical synonymously. What is the oscilloscope showing? It is a visual or optical representation of the time dependent, meaning how does it depend on time? How does it change? Time dependent, time varying, those are synonymous. Okay, it's just how something changes with time. Right. Then we have the spectrum analyzer that you also looked at on your learning activity. Again, if this is a standalone box, it would have an electrical signal in, and the output of the spectrum analyzer would again be something you're looking at. So it's visual or optical, okay? And it's a view of the time varying, right? How it changes in time or time dependent frequency content of the signal. All right, and then the last one that's on here is the function generator. So let's put our function generator in here. Okay, what does the function generator produce? It produces an electrical signal So like for an example, in class, when I had the box hooked up to the loudspeakers and I was choosing different tones, different frequencies, that was a function generator. It is an electrical signal containing the generated signal. So how does that signal change with time? Okay, and the input, if it's connected with wires, will be electrical or it could be digital, depending on the type of function generator. Same thing with the oscilloscope and the spectrum analyzer. If it's just an app or something, then the input will have been digitized. But for our case, we will not worry too much about that. We're going to come back to those in a minute, but right now we're going to go on to Roman numeral number 2. Identify the functions of common devices. Okay, and what they do. So some of those we've already covered. Okay, but right now, so some of those things that are listed in number 2 we've already covered up here. But right now what I'm going to do is I'm going to draw, this is in the slides also and in your book, the picture of an old-fashioned like huge stereo system, sound reproduction system. So you might have a tape player, slash recorder. So I have to make my box bigger. Because usually the tape player and the tape recorder are in the same box. Okay, and then you would have a different box that is the CD player, and then a different box that is the, the radio tuner, the AM/FM radio tuner. Okay. And then you also could have like a record player if you go way back, right? All right, and then those things are all connected via wires to an amplifier where you could select, which box you actually want to get the signal from, and then you could also tell the gain or the balance. There are all these different kinds of things that you can do in the amplifier box, each of which is a transducer, and then that signal gets sent to, let's say we have a stereo system, so we'd have 2 loudspeakers. And the loudspeakers would then generate the acoustical signal, the sound. Now, all of these places where I do these lines here in the middle in purple, I'm going to make my acoustical signal a different color. That's maybe pink. Okay. Oops. Too much pink. Okay. Right, so all of these purple lines in here, okay, these are all wires. So they are all electrical signals. All the purple lines here are electrical signals. Okay, so that kind of shows you the output from all these boxes is electrical. All these boxes on the left. The input to the amplifier is electrical. The output from the amplifier is electrical. The input to the loudspeakers is electrical. The output from the loudspeakers is acoustical. Okay, now over here on this side, I'm going to do different input signals in different colors. Okay, so into the tape player, oh, that's a nice arrow. Into the tape player, the input for the tape player is magnetic information. Okay, the input to the CD player is the optical signal because there's a laser that's reading the little divots off of the CD player. Okay. The input to the AM/FM box, the radio tuner box, is an electromagnetic wave, a radio wave, which is also a form of an optical wave, but let's see, and then the record player, right? It is the mechanical motion of the needle. That is the input for the record player. And then the output from all of those is electrical signals to the amplifier. Output of the amplifier is electrical, and output of the loudspeakers is acoustical. Okay. So that will hopefully give you the answers to questions 3 to 6. Question 3 is the magnetic player. So question number 3 takes magnetic in and electrical out. Okay. Question 5 is the CD player in. Input signal is optical, and the output is electrical, which is B. Okay. Number 6 is the amplifier, which takes electrical in and then a modified electrical signal out. So those are questions 3, 5, 6. Let's consider now the case of the tape recorder. Okay, so we have a tape recorder box. This is number 4. Okay, so the tape recorder is trying to record sound, so it actually has to be connected to a microphone. Okay. The input to the microphone will be the acoustical signal. It's connected via wires to the tape recorder, so there's an electrical signal there. And then the output, the thing that's being saved by the tape recorder, is a magnetic signal encoded on the tape. So number 4 would be taking in electrical and outputting magnetic. So let's see. Okay, so thinking of the microphones and the loudspeakers separate from the other transducers that are in the system. Okay. All right. All right, so now let's do Roman number 3. It says identify the purpose of some instrumentation systems. Okay, so in this case, you'd have some boxes strung together. Let's say, like we drew up there with the tape recorder, but let's say we have a microphone hooked up to an oscilloscope. Okay, the input energy to the microphone would be acoustical. Then it gets changed to electrical. And then it gets displayed as a visual or optical. Right. Okay, and what are you seeing? So if you were asked, what is the purpose of hooking a microphone up to an oscilloscope? You would be viewing the time-dependent or time-varying wave or waveform. So that's the why. Why would you do this? What are you seeing? Okay. Now let's say you have a microphone hooked up to a spectrum analyzer. That spectrum analyzer would give you a visual signal out again, something you're looking at, acoustical signal in. And why? You're viewing the time varying or time dependent frequency content of the sound. If we take these same 2 boxes, if I copy and paste them down here, okay, I could replace the microphones with pickups. If I replace the acoustical signal with the mechanical motion of a string. Mechanical motion of the string going into a pickup. Okay, and then if I hooked that pickup output into an oscilloscope, I would still be viewing the time-dependent waveform, but now it would be on the string. And here on the spectrum analyzer, I would be viewing the time-dependent frequency content of the string motion. Or the wave on the string. Or the string motion, whichever way makes more sense to you. Okay, so if it's acoustical in, then the oscilloscope would be viewing the time-dependent waveform of the sound. And the spectrum analyzer would be viewing the time-dependent frequency content of the sound. But if it's the mechanical motion of a string into a pickup, you're still looking at a wave and the frequency content of the wave, but now it's the motion of the string that is the wave. Okay, let's do a couple more examples. Let's say that you have your input is an MP3 file. Okay, so that's a digital signal that's going in. Okay. That would have to go into a digital to analog converter that then could send it to a loudspeaker that would then produce the acoustical signal or the sound. Okay, why would you do that? What was the purpose of that? Okay, that would be listen to sound stored as in the MP3 file. All right, now if we had sound, I'll just do the opposite. If you had the acoustical input energy into a microphone, and that microphone went into an analog to digital converter, okay, then that output would be a digital signal. Now, why would you do that? That would be storing sound as a digital signal. Something like, for example, wave, or there's all sorts of things, but we'll just call it an MP3 file, for example, right now. But any kind of digital signal. Okay. Let's try another one. Let's say we had a function generator hooked up to a loudspeaker. The input to the function generator, okay, would be an electrical signal. Could be digital, but we'll just use electrical for our class. Sends a new, whatever your input, sends the generated signal here as an electrical signal to the loudspeaker that then produces the acoustical signal. Okay, and that would be to generate sound corresponding to the function generator inputs. So that gives you some examples of why these transducers. Okay. Now I want to just say one word. We're going to talk about these systems in great detail later on, but I just want to say one word about your ears and then your voice. So your ears. What is the input energy for the ears? So the acoustical signal, the sound, is the input to the ears. There are lots of different pieces, mini transducers inside the ears that we'll talk about later. But if we consider the ears as a whole, it takes in acoustical energy and outputs a nerve signal, which we will also in our class refer to as physiological energy or signal. Okay. And then let's consider the voice, the entire voice as a single transducer for now. We'll break it apart into parts later. But in this one, you have nerve signals / physiological information or action, okay, that then makes the vocal folds vibrate, that makes the sound wave that travels through your vocal tract that eventually produces the acoustical signal. Okay, so then this goes back to our idea of the ears being an acoustical receiver and the voice being an acoustical generator. And we're going to talk about those transducers of our ears and our voice in great detail in Unit 2. But but right now we'll just consider them at that level. Okay, hopefully that was helpful for you.